Hello everyone. I'm going to talk through two examples where I will be verifying trig identities. And remember, an identity is just an equation where the left-hand side and the right-hand side are equal to each other no matter what the value of the variable is. When we're verifying trig identities, we have lots of different methods we can use. In these two examples, some of the methods I will be using are rewriting in terms of sine and cosine. I will be using some Pythagorean identities, and I will also be using just some algebraic operations like combining fractions together, things like that. Now, one really important thing that we need to note in the very beginning is that because we're trying to verify this identity, I need to show that one of these sides of my equation is the same as the other side. So what that means is I can't treat this like a normal equation and do operations to both sides. I want to do all my operations to one of the sides and show that I can basically simplify it so that it matches up with my other side. A good kind of method is to start with the more complicated side. So in this case, my left-hand side is more complicated. There's more going on here. I want to get this side of my equation to look like the cotangent squared of theta. So this side, my right-hand side, is going to stay the same the entire time. Okay. So first thing I'm going to do is I'm going to start with the more complicated side. And I am actually going to rewrite these in terms of sine and cosine. So the secant squared of theta times the cotangent squared of theta minus 1. Let's take these two trig ratios and let's rewrite them. So secant is 1 over cosine. So 1 over cosine squared of theta. And then the cotangent squared, that is the same as cosine squared divided by sine squared of theta. Still have that minus 1. And as I said, the second side, this is just staying the same. Multiplying these two fractions together, we have a cosine squared on top and bottom. So cosine squared in the numerator and denominator will simplify to 1. So we end up with 1 over the sine squared of theta minus 1. 1 over the sine squared, we have a basic trig identity, one of our reciprocals. This is the same as the cosecant squared. And then our last step here, I'm going to use one of our Pythagorean identities, cosecant squared minus 1. That is equal to the cotangent squared. So we end up with cotangent squared of theta is equal to the cotangent squared of theta, and now my identity is verified. Okay? So the right-hand side here stayed the same all the way through, but then on the left-hand side I have a series of expressions where I'm just using some different operations to maybe rewrite, simplify. Then down here we use the Pythagorean identity, and we showed that the two sides are equal to each other. Okay, let's do one more. So my second example, 2 secant of x is equal to the cosine of x divided by 1 plus the sine of x plus cosine of x divided by 1 minus the sine of x. So again, a good method. I'm going to start with the more complicated side. So I'm going to start with these two fractions here. These are already in terms of sine and cosine. So the first thing I'm going to start with is I'm going to combine these two fractions together. So our left-hand side is the one that's staying the same. And then on the right-hand side, to combine these fractions together, we do need a common denominator. So for this first one, we need to multiply numerator and denominator by 1 minus sine. So I have the cosine of x 1 minus the sine, and then we'll have both of these in the denominator. And then for our second fraction, we need to multiply the top and bottom by 1 plus the sine. So cosine of x, 1 plus the sine of x, and then our common denominator. Okay. So now for each of these fractions, we have a common denominator, so we'll combine them together. I'm going to do a little bit of simplifying here. I'm going to distribute the cosine of x for both of these fractions. So 2 secant, that's staying the same. So then these two distributed, we have the cosine of x minus cosine times the sine, and then plus for our second one we have the cosine of x again, and then this time it will be plus cosine of x sine of x. And that's our numerator, so we got a big fraction here, and then our common denominator 1 plus sine of x and 1 minus the sine of x. Okay, a couple things we're going to do next. We have some like terms in the numerator that we can combine together. I have a cosine and a second cosine, so that's 2 cosine of x, negative cosine, sine, positive cosine and sine, so a negative and a positive, that will give me 0. And then the second thing you want to do here is in the denominator, let's multiply this out. So these two sets of parentheses they're almost the same. The only difference is one is positive, one is negative. This is the difference of perfect squares. If we were to multiply this all out, we would see that the middle terms cancel each other out. So we end up with 1 minus the sine squared of x. Whenever I see 1 minus the sine squared of x, or something that's similar to that, I know that I can use a Pythagorean identity here. Cosine squared plus sine squared gives me 1, so that means 1 minus sine squared. Using my identity, that is equal to the cosine squared of x. And now we're getting close. We have 1 cosine on top. This is the same as cosine times cosine. So one of these will simplify. So we have 2 secant of x is equal to 2 over. So one of those in the denominator cancels out, so we are just left with 1. And then the last step, using our reciprocal identity, 1 over the cosine, that is the same as the secant. So again, taking a look at this, the left-hand side, that one stayed the same the entire way through. I'm not doing any operations where I'm multiplying both sides or anything. This side stayed exactly the same. In all my operations, I was doing to one single side. So we did some just basic algebraic operations to combine these fractions together. We had a Pythagorean identity here where we could swap this out with cosine of x, and then it was just a little bit of simplifying, and then our reciprocal identity at the end. So 2 examples of verifying identities, just using some operations and some trig identities.